Good day everyone. Today we will discuss Laplace Transform. So Laplace Transform is in the form of function x and convert it into function of s. So Laplace Transform takes a function to a different type of function. The function of s defined to be the improper integral of e raised to negative sx f of x multiplied by dx, evaluated from 0 to infinity. Since it's an improper integral, we're going to have question like kano saan ni siya mag-converge o kano saan ni dili mag-converge. So converge occur when the limit of integral of e raised to negative sx f of x dx from 0 to r where r approaches infinity. If this limit does not exist, the improper integral diverges and f of x has no Laplace transformation. Now let's proceed to the properties of Laplace transform.
So we have if Laplace transform of f of x is equals to the definition of Laplace, which is the integral of e raised to negative sx f of x dx from 0 to infinity is just equals to f of s. Then Laplace transform of x raised to n f of x is equal to the integral of e raised to negative s of x multiplied by x raised to n f of x dx from 0 to infinity. And this is just negative 1 quantity raised to n multiplied by the nth derivative of f of s with respect to s. So, Laplace transform of x raised to n f of x is just equals to negative 1 quantity raised to n multiplied by the nth derivative of f of s with respect to s, where n is equals to 1, 2, 3. So, how did it happen? So, from this, we have to substitute x raised to n f of x to this f of x. So, that's why we have this negative s of x and dx. We have to find the Laplace transform of f of x, then we have f of s multiplied by negative 1 raised to what's the given n. So if you have for example, you have negative 1 raised to 2 f of s. Then for this, you have to differentiate your f of s twice since n is 2. So Laplace transform of e raised to ax f of x is equals to the integral of e raised to negative s of x times e raised to ax f of x dx from 0 to infinity is equals to the integral of e raised to negative s minus a times x f of x dx from 0 to infinity. So Laplace transform of e raised to ax f of x is equals to f s minus a. So this time we have the function of x multiplied by e raised to ax. Your formula is that you have to find the Laplace transform of f of x and then shift your s domain with f s minus a. Depending on the value of a and a raised to ax. In other words, you'll shift your s frequency by a units. This is it. So if you have this Laplace transform of e raised to positive ax, then you have the f s minus a as the shifted part. But if you have the negative exponent here, negative exponent, then the shifted part or form is positive. For example, we have Laplace transform of x cubed times e raised to 5x. So rearranging, we have Laplace transform of e raised to 5x multiplied by x cubed. So our x cubed here is our f of x. So we have to first find the Laplace transform of f of x. So we have to find this Laplace transform of x cubed. So Laplace transform of x cubed is equals to n factorial over s raised to n plus 1. 3 as our n over s 3 plus 1. So we have this, and our f of s is equals to 6s raised to 4. Since our a in the problem is 5, we have f s minus 5 is equals to 6 over s minus 5 raised to 4. In order to understand the Laplace transform, we just need to recall this. The derivative of the sum is equals to the individual sum of the derivative. We can also pull out some constant. See. So, same with the integral. The integral of f plus g from a to b is equals to the integral of f from a to b plus the integral of g from a to b. And we can also pull out some constants. So, yeah, this is understandable. So, this is the constant. So next is if Laplace of f of x is equals to f of s, and if limit of f of x over x exists where x is greater than 0, then Laplace of 1 over x f of x is equals to the integral of f of t dt from s to infinity. The function f of x is of exponential order, and as x goes to infinity, if the absolute value of f of x is less than or equal to me raised to cx, m and c are constant for sufficiently large x. If we try to compute the limit of f of x over e raised to cx as x goes to infinity, if the limit exists and is finite, usually 0, then f of x is of exponential order. In exponential order function, we can see the uniqueness and existence of Laplace transform. The next theorem, if Laplace of f of x is equals to f of s, then Laplace of integral of f of t dt from 0 to x is equals to 1 over s f of s. The Laplace transform is applied to integrals of functions. If f of t is a piecewise continuous and the absolute value of f of t is less than or equal to m e raised to at, like from the previous one, m and a is constant for sufficiently large t, or from the previous one, x. If f of t is a piecewise continuous and the absolute value of f of t is less than or equal to me raised to at, then we have this one. So, what is a piecewise continuous? A function or curve is piecewise continuous if it is continuous on all but finite number of points at which certain matching conditions are sometimes required. So, it depends on the conditions required. So, this is the last property. So, it says that the Laplace transform of the periodic function f of x with period omega is equals to the integral of e raised to negative s x f of x dx from 0 to omega divided by 1 minus e raised to negative cosine. So this depends on the periodic given. Functions of other independent variables. From the discussed properties of Laplace transform, we have noticed the definition of Laplace transform are presented for functions of x. It is for consistency only, but it can also be applicable for other independent variables. You just have to replace the variable x by any variable of interest, like from the properties we have. So we have this from the previous one. So our variable of interest is t. So we can have replace x by t. We have this is the counterpart of this one.